Okay, good morning. So today we will introduce the final assignment for the exam. So here is the assignment. So basically the idea is that you have to write a simulator in C++ using a library called MetaSim, a library that I wrote very long time ago. And this library is available at this address, so on GitHub. Of course, you have to study the library. It's quite small, so not many things to study. There is some documentation, not very up to date, but it's not very difficult to use because there are some examples. You study the code, the examples, you try to understand how it works. Of course, then you have to use this library and write extra classes for modeling the problem that is described in the exercise. Okay? If you find bugs in the library, it has already been used last year, so not many bugs came out of it, so it's probably okay. Also has been used in many other projects, so it should be quite stable. But anyway, if you find bugs, please tell me. Okay. And the deadline for delivering the project is just before the exam. So if you plan to come in the first date of June, that is 16th of June, you should start quite early to think about this project, of course. So the idea is that you have to simulate a wireless communication protocol at an abstract level of detail. So I don't ask you to simulate the protocol in very fine details, but at a very abstract level. So if you want to have a reference, you can think of wireless protocols like, for example, the Wi-Fi protocol or the ZigBee protocol for WSN. But it's not really important. I want you to abstract away from the protocol details as much as you can, but still implement some basic features. In particular, I want you to implement the fact that this wireless node that communicate with each other have a limited communication range, so they cannot communicate with very far nodes. And you should simulate collision interference because of the shared communication medium, and you should simulate the problem, the hidden terminal problem. So let's start describing the model. So basically, you have to assume you have a certain number of wireless nodes, and these wireless nodes do not move; they are fixed, and they are in a 2D space. Okay, and every node can send and receive messages using a single shared communication channel. You can assume that the 2D space is empty, so there is no reflection at all. That there is a fixed communication range. So one node can communicate and maybe interfere with nodes within its own range, but cannot communicate and cannot interfere with nodes outside the range. Okay? We don't need a very realistic model, the physical model of the channel. So basically, you have to assume a circle with a center on the node and with a certain constant radius. All the nodes inside the circle are reachable, so you can communicate with them. All nodes outside the circle are not reachable. Okay? So basically, you have to assume a constant communication power all over the circle and on-off effect. If you're inside, you can communicate. If you're outside the circle, you cannot communicate. Also, you can assume that all the radius are the same, so all nodes have the same communication range. So quite simple. However, you must model interference. If two nodes send a message at the same time, all nodes within the intersection of the two circles will not receive the message correctly. Okay? So if I'm sending a message to node A and another one is sending a message to node B, but for some reason both A and B are within the reach, then there is collision and interference. And so basically nobody hears anything. So you have to write a very simple protocol. Every node hears the channel before sending the data. If the channel is not occupied by anybody, it can start sending soon after, whatever it means. You choose whatever you want for this soon after. Okay? So basically you have to write classes and functions that model the system. And of course you have to write tests to show that every class is working as expected. Okay? So you have to, for example, make a class that is called node, another class is going to be called message or packet, and you have to understand if two nodes are within the same radius and so on and so forth. You have to need a list of nodes in the system and so on. The second part is writing a simulation. Once you have everything in place, I want you to run a simulation. So the simulation is that you have a matrix of nodes in the 2D space, and they are organized as a grid, a rectangular grid, okay? Actually a square grid. And every node and in its range only the 4 immediate neighbors. So every node, for example, node 2, 2, as in its range node 1, 2, node 2, 1, node 3, 1, and node 3, 2. Okay? So it's the north, south, east, and west nodes are in the range. The others are outside the range. Okay? Every node is identified by its geographical position in the 2D space, expressed with the x and y coordinates. And each node in the first column tries to periodically send a message of one single packet to the corresponding node in the last column. And each node in the top row tries to send a message to the corresponding node in the bottom row. Okay? So 1, 1 tries to send a message to node 1M, node 2, 1 tries to send a message to node 2M, and so on. And also node 1, 1 tries to send a message to node M1, and node 1M tries to send a message to node MM, and so on. Okay? So all the first row sends a message to the last row, and the first column sends messages to the last column. Okay? You can assume static routing tables. I don't care about routing. So basically every packet will contain the coordinates of the destination node, and every node knows where to forward every packet by using these coordinates. So I don't need routing. Okay, you just look and you understand where you have to send the packet. Of course there can be collision. In case of collision, the message is simply lost. Every sending node sends a total of 100 packets with a certain fixed period P, and after that it stops. So you run the simulation for some time. After every node finishes sending the packet, you stop the simulation, and you have to measure the number of messages that have been received by the receiving nodes in total. And you have to vary the number of nodes and vary the sending period and measure how much message in percentage are received with respect to the message that have been sent. Okay? Now remember that every simulation must be completely reproducible. You have to be able to redo the experiments exactly and obtain exactly the same result. So if you plan to use some pseudo-random numbers, make sure that the pseudo-random generators can be initialized with a certain well-defined seed. So you can redo the experiment whenever you want. Okay, so this is the project, and everybody has to do that. And for the students that are doing the 9 credit course, so basically the students of the Master of Science and Embedded System, there is an extra requirement. I want you to implement a graphical interface to this simulator using the Qt library. So basically, you must implement an interface with dialog windows and forms set up on experiments, nodes, positions, whatever. A way to save and load an experiment setup. The interface must show the nodes in the 2D space and the distance and the communication ranges to understand if every node has anybody in the communication range. And finally, the interface should allow to run a simulation offline, show the results in a separate window. Okay, it should be possible to do everything that is asked in step 2 with the GUI. For example, show a graph of the dependency between period and number of collision received messages. Okay, so it's a little bit long, but not impossible. And as I said, it has been done last year, pretty much a very similar project, except the last part of the graphical interface. So it's doable. I'm going to show you how to use the MetaSim library. So basically, you have to download the library from here by using JIT. So I think you can install JIT on your system, which is not very difficult, and you can clone the library and use that into your download that in your system. Or otherwise, you can just download the zip file and then unpack it and have it in your system. Once you do that, you go inside directory metasim and you run, as first thing, you run auto reconf. This is a preliminary thing for configuring your system. Then you run a configure and then make. And of course, this is already compiled, so everything is okay. And then you go inside directory examples, and you find 3 examples of using of this library. So one is a simple MM1Q, another one is a Markov chain, and finally the last one is a very, very simple Ethernet network. So you could start from this Ethernet example to generalize it to a wireless protocol. So let's see, first of all, the Q example, which is the simplest one, and explains to you a little bit how to use the library. Okay, so let's open first the HPP file. Okay, actually this is not needed anymore. It's a very old thing that is used for compiling with Microsoft C, but you can remove it right now, okay? The library is contained in this metasim.hpp header file, and particle uses the observer pattern we have seen before. Anyway, most of the things are in this metasim.hpp library. You find the header file here in sources. And metasim is just an inclusion of basically all the important header files in the library. And I'm going to explain to you the meaning of these header files in a little while. For the moment, let's say that most of the things are enclosed, most of the definition in the library are enclosed in these 2 namespaces. So if you want to use it, you should start with using namespace methods. If you want to simulate something in the library, you should derive your class from the entity class. So entity in this library is something that needs to be simulated. It's a part of the simulation. So for example, here I'm modeling an MM1Q. MM1Q is consists of a node, and node it's a generic class, and special kinds of nodes are sink, which just consumes packets, source, which produces packets, and finally queue, which actually simulates a queue which can receive a packet and serve it with a certain service time. Then you can define statistics, but we are going to see it later on. So everything that that you need to model should derive from entity. So entity is the class that actually models something that needs to be simulated. It's mandatory to redefine these three functions, actually these two functions, new run and end run. I will explain what they do in a little while. Right now, you have to know that these are virtual functions defined inside the entity that needs to be overridden. As I said, this is a node that represents a sink, and this is a node that represents a source. And so the idea is that you connect sink, queues, and sources to make up a system. And here in the queue.cpp we have the main. In main, the user asked to introduce two doubles, lambda and mu. Lambda is the rate of generation of arrivals, and mu is the rate of generation of services. Okay. Okay, so you do lambda and mu. Lambda is, as I said, arrival, and so lambda cannot be larger than mu, otherwise the queue is up indefinitely, and so the system is unstable. You can define random variables, and in particular I'm going to define two variables here. Exponential var is a random variable of type exponential, with exponential distribution and with parameter lambda. And at is another exponential variable with rate mu. Then I define a sink, a queue, which is the MMM1Q, and a source. Okay, and the constructor, I just connect everything. So basically the queue has as input this sink. Then it uses the st exponential variable for the service time and has this name. And the source will send packets to the queue. So basically it sends packet to the queue, it generates packets with arrival time at, and it's named the source. So basically source will generate packets, will send them to the queue, and the queue will process it with this service time and send to the sink. We want to compute the average waiting time for a packet to be served by the queue. How we do that? So basically we are going to compute the average length of the queue, average queue size. Okay, and we define this, which is has been implemented in the HPP file, and I say that this one should be attached to the source. So when we produce a packet, we'll measure the length of the queue. Then we say that we are going to set up a running time, and we want to discard the first 2000 samples of this statistic, because at the beginning, of course, there is a transitory, and so we want to discard the transitory. Okay, this is just for debugging. The debugging output is going to be put into the log.txt directory, and I'm going to debug everything. And finally, I just run the simulation for so much time, and I run it 8 times. So this is going to run the same thing 8 times. And finally, I get the statistics, which are the average queue length and the confidence interval of this measure. So let's see what happens if I compile it and I execute. So this wants the lambda. For example, lambda is going to be 10 and mu is going to be 20. And then it runs for 8 times the simulation, and then it's going to tell me that the average queue length is 1. So in average, when a packet is produced, it's going to find 1 packet in the queue, and the confidence interval is quite low because it's basically 1%, 1.6%. And I can run the same thing with the different parameters, of course. For example, I can make lambda and mu closer to each other, and then in this case, the average queue length is much higher because the service time is very close to. Okay, so okay, so how does it work? What does this sync queue and source do? So as I said, the library is based on the fact that there is this notion of entity, and the other important thing is the notion of event. So the 2 most important classes in the library are entity and event. Entity is something that needs to be simulated. Okay. So for example, I'm going to simulate a node, and so a node is an entity. Then the sync is a very simple node, because the only thing that it does is to consume the packets it receives. So basically, function put is a function that is called whenever a packet is inserted into this node, which is a sync. So it just measures the number of consumed packets, so increases this variable. And every time I run a new simulation, I reinitialize consumed event. So sync is a very, very simple class. Source is a little bit more complicated because it uses random variables for producing the packets, and it uses it needs to send the packets to a destination node. So I can send these packets to a queue, and it uses also the notion of event, and in particular it needs to produce these events at the certain times, and these times are decided by the random variable. Okay, so internally to source I define another class which is called produce event, which takes this class source as a reference, and it initialize n, and he has to override a function called doIt, which is called every time the event is triggered. And what it does, it will call the produce function of source. This is a very simple function. Just to make things simple, I'm going to re-edit the thing here. Let me see a little bit better what's going on. Okay, so this is a very simple class. It's an event class, and I declare an event which I call prod event of type produce event. So very simple. Then I have my source, which I initialize the destination node, I initialize the random variable and the destination and the produce event by passing this as then I have a function put, which does nothing because I cannot put anything in this source. Then I have a function produce, which is called whenever the event is triggered. So remember that produce event will call the produce function of source. And so this will in turn call the put on the destination. So for example, I'm putting a packet in the queue, and then it will call this function of event, which basically posts a new event of the same type, produce event, in the future, when at the current time plus a certain number, which is a random sample of variable AT, arrival time. So remember that arrival time is a random variable, which I just created, and tick is just a transformation of this sample, which is a double, into an integer, so a tick. Okay, so it's just a conversion. And of course, at the beginning of every simulation, I have to post the initial instant at which the produce event has been is posted. So the first initial event has to be posted at the beginning of every simulation. And that's it. There is nothing else to say and to do from this. And finally, the queue is quite simple because it takes a destination node. Internally, it uses a dayqueue data structure for modeling the queue. And it uses a random variable for the service time. Okay? So let's see how does it work. First of all, again, I have an event, which is the service event. Very similar to produce event. It does nothing but call the queueServe function inside the queue. Okay, so very, very simple. And I define an object of type service event. And here is the queue in which I initialize the top node, the top class, then initialize the destination, the internal queue, the service random variable, and the service event. Then this is a function that is called from the source. So the other class, source, will call this put to insert an element into the queue. So I just push back the constant 1, so a new packet has arrived. Now, if this is the first one to be inserted, I post a service event at a certain future time. Okay, so I extract a random sample from service time, I add the current time of the simulation, and I post a service event into the future. Then serve instead is called by the service event, which means, okay, the service time has elapsed, so now it's time to remove the packet from the queue. If there is another packet, I post another event, otherwise I don't do that. And finally, I call the destination put, because I need to put the packet in the destination. That in this example is a simple sync, but it could be another queue, for example. And finally, get sides, it's for getting the current sides of the queue. New run, at the beginning, I clear the queue, and I wait for the first packet to be inserted. Okay? So this is basically our model. Not very complicated. I just have a couple of events, the service time and the arrival time events. I have 3 classes that model 3 different kinds of node, and the most important is the queue, and that's it. Statistic. How do I take the statistic? Well, the statistics are things that are to be attached to events, and they are called the probe function of a statistic class is called when a certain event is true. And I can call record to record one more thing. So basically, I'm going to call the q get size minus 1. So I take the size of the queue and I record it. Okay. So this one is called when source puts a new packet into the queue. Okay. So I record the size of the queue minus 1 because the new packet has just been inserted. If I want to know how many packets were in the queue before the packet was inserted, I have to subtract 1. Okay. And finally, this is the way to attach the statistic to the event. Basically, I have to create this new thing here, and that's it. That's the only thing I need to do. If you go and look at this code, it's very similar to the observer pattern we have studied during the course. So I invite you to open this file, particle.hpp, and look at the code, and you will find pretty similar code to the one that we have studied during the lecture, a couple of lectures ago. Okay, so that's it. Of course, we can also change our simulation here. Here we have just one queue, but we could make, for example, two queues, one after the other. So, for example, I can produce another queue. And then I can connect this to queue and this to Q2. So now I have two queues in one after the other. So this one sends to Q2, Q2 sends to Q, and Q sends to sync. Okay, and well, maybe I would like to measure how many packets are. What's the length of this when I actually produce something. So one thing I could do is to, how I define the average queue size. Average queue size takes a queue takes a source, sorry, so I cannot do that. Okay, so anyway, I don't want to change too much the meaning of this, so I'm going to just measure the average queue size of the first queue. Okay, so just to tell you that everything works because it's been made modular, but of course you can change as much as you want. Okay, so whatever.
Excuse me, Professor, can you
Yes.
The passages for the configuration of the metasim folder of the metasim?
Yes, basically you unzip,
okay,
and then you go here and you type auto reconf, and then you type configure, and then you do make. So I'm going to remake everything. To do this, you need if you have Linux, you need to install a few packets actually. I don't know, I have an Ubuntu distribution, but in other distribution is going to be pretty similar. So what you have to do is to install the auto tools. that's not the right one, sorry. So the Auto Tools collection is a set of tools that make it easy, relatively easy, to build and install programs from a source distribution. So you have AutoConf, AutoEater, AutoMake, AutoProject, AutoReconf, AutoScan, and blah, 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 blah. So what you need is AutoReconf. Then after that, you do configure and then make and make install. And then if you want, you can do sudo make install. Okay? Or otherwise, if you want to use your preferred IDE, you forget about the AutoConf and you just includes all files that are contained in the source directory into your project. So you go into the source directory, and you take all the CPP and HPP file, and you include in your preferred IDE. Okay? What kind of IDE to use? I don't know. There is Eclipse with the CDT. Sorry. So one is this one. It's the version of Eclipse that works with the C, C++ development tooling. And it should work in basically both Windows, Linux, Mac, hopefully. So you download and everything should be okay. Or otherwise, there are other IDEs. Of course, if you have a Windows with Visual C++, you can use Visual C++, or you can use other kind of development environment. There are many that you can use, okay? The important thing is the compiler, and try to make sure you have the right compiler for compiling. Okay. Okay, so this is pretty much everything. You have to know about the MetaSim library. I invite you to, in the future, in the next weeks, to go and look a little bit at the libraries. And I think next week we will take some time to analyze the other example, which is the ETH example, where I show you how to set up a sort of a very elementary version of Ethernet, a model of a simulator for Ethernet. Okay. So today we just stop here. So I uploaded the assignment on Didactive, and please have a look at it. Most probably there are many things I forgot to specify. So if you have doubts, please tell me, and I will try to correct the specification, or we can discuss something on how to do the different parts of the project. Okay?
Sorry.
Yes.
The project is for one person or for a group of two persons?
No, I thought about it. So I think you can do that in pairs. So basically, groups of 2 people.
And
of course, let me know.
Is the same?
Sorry?
If I do myself, it's the same for you?
Yes, yes. Okay. So maximum 2 persons, so minimum 1. Okay, so you can do in group, or you can do a single. Okay, that's it. I just do a little break before continuing the lecture of yesterday on template metaprogramming. Okay, so let's do a very short break, let's say 10 minutes.
Professore, posso chiedere
Sì.
una cosa? Praticamente l'esempio che ho fatto vedere della Q, il sync inserisce i dati sulla Q sostanzialmente e la source è quello che li preleva dalla Q.
Sì, in realtà la source non li preleva, gli vengono inviati, cioè la source è quelli che li manda alla queue, quindi chiama la put della queue.
Ah, ok. Ah, la source è, quello che è quella che inserisce nella Q.
La sorgente, quindi è quella che genera i pacchetti dal nulla e li manda alla coda. La coda li processa con un certo service time e poi li manda al sync. Il
Ah,
sync li prende e li fa sparire.
Scusi,
Sì,
ho dei problemi a compilare Metasim.
sì.
Il log degli errori lo posso mettere tra i commenti su YouTube oppure lo chiedo in inglese?
Sì, sì, me lo mettono sui commenti su YouTube.
Ah, ok.
Su YouTube oppure anche sul GPU se ce l'ha.
Sì, sì, ok.
Oppure per email, tanto sono qui, quindi lo vedo.
Ah, vabbè, magari in un posto dove siano raggiungibili da tutti.
Sì.
Ma ci sono problemi a compilare Metasim con Qt Creator su Windows?
Con Qt Creator? Non
Sì,
credo.
con Windows però.
No, non credo.
Ok, sì. Va bene, io ci provo in ogni caso, poi se ci dovessero essere problemi in caso io lo faccio sapere.
No, comunque diciamo Metasim è proprio standard C++ anche vecchio, nel
Ok,
senso che non è che l'ho toccato molto per farlo compilare col nuovo, quindi dovrebbe funzionare sia col vecchio che col nuovo.
va bene, va bene.
E deve
Grazie.
funzionare dappertutto perché è stato testato anche sui vecchi compilatori Windows. Penso sui nuovi compilatori Windows non c'è. Comunque Qt Creator su Windows non lo so su cosa si appoggia, eh. Devi andare a vedere quale compilatore usa.
Sì, c'è QMake, si può impostare con CMake, si può
Ma quello non è
configurare.
il compilatore alla fine è o Clang o, o GGC,
Sì, GCC 11 si può impostare.
oppure può essere configurato per utilizzare Visual C++.
Sì, 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 va bene.
Quindi se dovete fare il progetto, siete diciamo dei 9 crediti, vi consiglio di utilizzare Qt Creator in effetti.
Sì. Ok, sì, vabbè, perché poi l'interfaccia grafica si fa direttamente da...
Sì.
Bisogna passare in ogni caso da qui. Va bene. Grazie.
Sì, sì. Okay, you send the message. Yeah, you send the message.
If you left, but you need to choose, right? Sexto. Vediamo se riesco. Code model. Although it's very easy on the job.
Okay, so we continue. We continue where we left yesterday. So let's have a little bit of recalling of what happened yesterday. So basically, we started by describing a few techniques for using templates for metaprogramming. What does it mean, metaprogramming? Metaprogramming means programming with a compiler. So basically using some tricks for making some calculation at compilation time. So while the compiler is compiling, it does some calculation for us and configures the code for us. This is useful every time we want to optimize the code, our template code, for by specializing on the types. So we have seen some tricks, for example this one, in which we obtain one different type for every integer. And we use that for doing what is called a compile time dispatch. So depending on the value v, whether this is true or false, this produces two different types, and then we use those types for selecting which function to call. So we said that the example of the container where we want to copy, and the copy can be through polymorphic, through a clone when the class is polymorphic, or it can be through the copy constructor. So when this is for a polymorphic type, we have to use clone, and when it's non-polymorphic, we have to use the copy constructor. But we cannot do that because both branches of the if then else are compiled, and so the compiler gives an error. So we are going to use the fact that only one of these two functions is actually compiled, and the function that is going to be compiled depends on which parameter here is the value of this type, basically. So if this type is into type true, then the first one is going to be compiled. If this type is into type false, the second one is going to be compiled and used. So we select the algorithm to be used for copying depending on a type, and this type is known as compile time, of course. So all of this is done by the compiler. So it's an if then else for the compiler. Okay, so I'm going to show you now one example of doing this using one example of using this kind of techniques for optimizing the code. Consider the code you have written for your first exercise. So intersecting two containers. You want to compute the intersection of two containers. Now, you should have realized that if the two containers are sorted, then the intersection is much easier. Okay? So, in fact, we are going to implement the algorithm in the following way. We are going first to sort the first container and sort the second container. And once they're both sorted, we are going to go through both of them with a single cycle. And we are going to select which one to insert in the result, which is here. Okay? So this algorithm is very nice, and but unfortunately, it works only for vectors. So here you have two vectors, and the result is going to be put in a resulting vector. So I first do a random shuffle of both vectors, then I print three of them, then I intersect, and finally I print the result. I have an error here. What's the error? I'm doing an intersect opt. Okay, so I have a problem here. I don't remember. I'm just trying to eliminate this. Okay, so it was just a wrong order of the functions. Anyway, okay, so let's go back to the example. So here I have an intersect function, which is has been optimized for vectors, so it works very nicely for vectors. Let's see how it works. Okay, so here you have the original thing that has been random shuffled, okay, more or less. You have 3 here, 6, 6, 9, blah, blah. You have also the duplicates. Then this is the sorted versions, and this is the intersection. Okay, so everything works okay. Unfortunately, if you try to use lists instead of vectors, this is not going to work because you cannot sort lists. And why you cannot sort lists? Because the sort requires the iterators to be random access iterators. And list does not support random access iterators, it supports only sequential iterators. So this function intersect cannot be used for list, unfortunately. So we have to write another function that works for list. So typically one would write things like this. Intersect I want to check that these actually the two iterators are random access, because otherwise I cannot sort. So I do what is called a static assert. Static assert is a check that is done by the compiler that a certain property is valid for a type. And in particular here we are going to check is random iterator tag A value. What is tag A? Well, tag A is this. So I think I already told you about this strange thing here, iterator traits. So standard iterator traits, it's a very simple class which contains just one thing, a type definition that is called iterator category. And this iterator category is one between random access, forward iterator, and things like that. Let's look at the definition of standard iterator traits. So it's a very simple class iterator traits. It's a template class. So the template parameter must be an iterator, okay? And it defines the properties of iterators. In particular, has a few members. The most important is iterator category. The first one is difference type. Type to express the result of subtracting one iterator from another. Then you have a value type, the type of the element the iterator can point to. Then pointer, the type of a pointer to an element the iterator can point to. Reference, the type of a reference to an element the iterator can point to. And then iterator category, that can be input iterator tag, output iterator tag, forward, bidirectional, and random. So we need to check that this is actually a random access iterator flag. Okay? And how do we do that? Well, first of all, this is what we need to say about the iterator category. I rename all of this, which is quite long, as tag A. And do the same for the second one. I rename it as tag B. And then I check, is random iterator tag A value? This one is going to be true or false. So it's going to be a type that represents true or false. And if tag A, so the iterator category of the first iterator, is random, then this is going to be true. Otherwise, it's going to be false. So static assert checks that I'm actually dealing with random iterator, and it checks this at compile time. Okay? So let's look also at the definition of this is random iterator. Sorry, I cannot find the standard. Okay, I cannot find it on the web, but okay, but anyway. Oh yes, I cannot find it because I defined it here. So it's a random iterator. Sorry. It takes a value false in general, and if it's a random access iterator tag, then it takes true. Okay, so this is a sort of simple way that I used for checking that the iterator is actually random access. So it's a technique very similar to the one we have seen yesterday, like this one, right? It's not very different. And actually, I'm using a template specialization. So this structure defines an enumerator which is normally equal to false, and then I specialize, telling that for this specific value of the template parameter, it should return true. So this one returns true or false depending on the type of the iterator. So is a random iterator will tell me if it is a random iterator or not. And static assert is a static assertion that is checked by the compiler. Okay? So this one compiles because I'm actually using a vector. So main calls a try vector, which is exactly the same code as before. But now let's try to use a list. So I comment this. And comment this. And I try to compile with a list. So the list, I give two lists and a vector as a result, and I try to intersect the two lists. Let's see what happens. Well, it gives me an error. So the compiler gives me an error. It tells me that in instantiation of intersect, error, static accession failed, cannot call intersect on a random access iterator type, which is exactly what I wrote here, including the typo mistake. Okay? So this is printed by the compiler when this static assertion fails. So at least I know I cannot use intersect on a list. Can I do better? Can, for example, I use two different versions of the intersect? One that is more general, it's going to work when the iterators are non-random, and another one which is specialized for vectors. Yes, I can do that, and in fact, this is the third implementation of this. So still I'm using is random iterator like before for specializing, for knowing at compile time if a certain tag is a random iterator or not. Then I use the optimized version. The optimized version, I adding two more parameters, type A and type B, and these are a general. And so I'm going, so this is not optimized at all. It's a generic version, okay? And so basically it does two for cycles, one inside the other. I'm going to insert the result into a temporary set, and then after the temporary set has been built, it takes all the elements from the temporary set and puts in the result res, which is this parameter. Okay, so it's not optimized because of the two for cycles, one's inside the other. And then let's take the optimized version instead. And as you can see, this is a specialized version of the first one. So the first one had 1, 2, 3, 4, 5 template parameters, and in particular type A and type B were two generic functions. And this one instead is specialized because the two last template parameters are a random access iterator tag. Okay, so this version is called when both are both sequence have random access iterators. Okay, and so it first sorts and then uses one single while cycle for intersecting. And finally, the intersect, it just calls the intersect opt by passing these two tags which have been obtained by from the iterators. Okay, So now everything works because I just call intersect, and depending on the fact that the first iterator and the second iterator are random access or not, the correct version of the intersect opt is going to be called. Not only the other one is not going to be called, is not going to be compiled, and so the sort is not applied to list because it's not even compiled. So here we have try vector and try list, and in the main I first try the vector and then I try the list. Okay, so the first one is still wrong, but this one should work. Okay, so vector and list, I have the same results. Okay, so I've shown you how to dynamically select one between two implementations of the same function, depending on the type that I'm passing to the function. So on the characteristics of the iterator. Okay. A few more details about this. The first detail is that I told you that the function that is not used is not even compiled. Actually, it's not exactly like this. It's a little bit more subtle. In fact, when the C++ compiler needs to select one between several versions of the same function, it needs to compile all of them before it can select which one to use. So actually, all functions here are compiled, both the first one and the second one, and both for the vector and the list. But only one of the two is used, and the other one will produce an error. Well, this error is not reported because of this property of the C++ compiler, which is called sFinae, that would read as substitution failure is not an error. So it's a language feature of C++, and it means that whenever the C++ tries to use one between several functions to understand which one to use, it compiles all of them, but then it just discards all errors if, of course, a good candidate is used. Here, for example, we have another example. We have two functions, multiply. The first one just takes integers, and the second one is a template generalization, which takes two parameters t and returns t multiplication results. And then in the main, I just use multiply 4 and 5, where 4 and 5 are two integers. So obviously, the first one is selected because it matches better than the second one. However, also the second one is compiled, and it would produce an error because int colon multiplication results doesn't make any sense. Okay, so during instantiation, an invalid type is produced, int multiplication result. Due to the property of sFinae, however, the invalid instantiation is neglected automatically. At the end, there is exactly one multiply function that can be called, so the compilation is successful. Okay, and this property is often exploited. So basically, you have seen one example here in which I have several intersect optimization, and only one is actually the one that's used. And if you have errors on the other one, this is not even they are not even reported. One last technique I would like to show you today is a technique that allows you to select types, and a technique for understanding if two types are related to each other. So let's start with this technique. It's quite simple. I think you should have more or less understood how to do this kind of tricks. But anyway, suppose that in my container we want to store objects if the type is non-polymorphic, and we want to store pointers to object if the type is polymorphic. So we have again my container. I'm going to pass objects. What I'm going to store in the object. I'm going to store objects, or I'm going to store the pointer to the object. Now suppose that internally you use a vector. What type this vector should contain? T or T star? Well, depends on if the type is polymorphic or not. So we make use of a select structure. This select structure comes in two specialization. The first one takes a Boolean at parameter t and the type name u, and it will tell you that t is renamed as result. And then you specialize select when the flag is false to take u as a result. So depending on the value of the first parameter, flag, result is t or result is u. So this select is again one implementation of an if then else. If true, result is t. If false, result is u. So your container, which is templatized with t and a Boolean that tells you if t is polymorphic, will tell you type def select is polymorphic, t star t result is renamed as value type. Now, if is polymorphic is true, the result is going to be t star, so value type is t star, and the vector will contain t stars. However, if is polymorphic is false, result is t, value type is t, and the vector will contain objects. So we have an if then else here, which makes value type equal to t star or to t. Okay? Of course, you can use this in many different ways. Let's look at another trick. It's how to detect inheritance relationship. Sometimes it's important to be able to understand if two generic types, T and U, are in a relationship of inheritance. For example, we would like to know if U derives from T. Okay? Of course, we want to know that at compilation time, not at runtime. At runtime, it's easy, let's say, okay? But at compilation time, is a little bit more difficult. And this may be useful in some cases, but anyway, it's also a very good exercise to understand how this template mechanism works. So how can we detect inheritance? Well, inheritance is a special case of conversion between pointers. In particular, there are only 3 cases in which we can automatically convert a U star to a T star. We can convert U star to T star when T and U are the same type. So if both U and T are integers, of course you can convert a pointer to integer to a pointer to integer, of course. But if U is a pointer to double, you cannot convert to a pointer to integer, of course. Unless you do an explicit cast. So first of all, T and U must be the same, or T must be a public base of U. If T is a public base of U, you can automatically upcast a pointer to U to a pointer to T. For example, if you have a function that takes a pointer to t, you can pass the address of an object u without any problem, because that is an upcast. So upcast is automatically. And third case is void when t is void. If t is void, of course you can convert a pointer to something to a pointer to void without any problem, because any pointer can be converted to void star. So if you want to detect if u is a derived class from t, so if t is a base class of u, we have to check if u can be converted to t, and we have to exclude the two other cases, if t and u are the same, and if t is void. So if you can automatically convert u to t, u star to t star, and t is not void, and u is different from t, then t is a base class of u. Okay? So now the problem is how to detect if an automatic conversion exists at compile time. So we are going to use size-off. Size-off is a compile time mechanism of C++ to compute the size of a type. And since this is done at compile time, its argument is not executed at runtime, but it's only evaluated. In particular, if you give size-off a function call, the function is not actually called, but it's only the return type is evaluated to understand what it is its size. So size-off does not execute any code. It is only a mechanism for the compiler to compute the size of the type. Okay? So remember, size-off does not execute any code. It's substituted with a constant by the CPP compiler. So what you can do is something like this. Int, return int. It's a function that you don't even implement. You just define, but never implement. And then you write size-off return int, which is equivalent to calling size-off int. It's exactly the same. Return int is not called, also because it's not implemented. It's just evaluated by the compiler to understand what's its return type and computing the size of this type. So size-off returns an integer, and you can use this integer in comparison. So we are going to define two types of different size for sure. We are going to define small as a char, and we are going to define big as two chars. So for sure we know that the size of big is larger than the size of small. For every compiler, for every platform, for every architecture of the processor, big has a larger size than small. We are sure about it. And now we are going to write our conversion mechanism. So as often happens in metaprogramming, we are going to write a class which contains nothing but the mechanism used by the compiler for doing the conversion. So this class needs to check if t is a base class, if t is a base class of u. Okay? And in particular, we want to see if u can be converted into t. So first of all, we define the small and the big data type. Then we define a function test, which takes a parameter of type u and returns a small. We don't implement this function, we just declare it. Then we take a function test, which takes 3 points, an ellipsis. This means that test can take anything. Doesn't matter the type, test can take anything. And we return a big. Okay? And finally, we take a function, make t, which returns a t. Again, none of these three functions is implemented. The only thing we care about is the parameter they take and the thing they produce. Okay? So, finally, we are going to define exist as a Boolean expression in which we compare the size of this type and the size of small. What is the size of this type? So first of all, we make a t. So the result of this make t is t, an object of type t. Then we try to pass an object of type t to function test. We have two versions of test. One that takes u and one that takes an ellipsis. So actually this is the other way around. We are trying to convert t into u. Sorry for the confusion. So we are going the other way around. We are trying to convert t into u. So we take t and we try to convert to u. If the conversion is possible, then the result of this test is going to be small. Small is going to be equal to small, so exist is going to be true. So if t can be converted into u, then size of small equals size of small, so exist is true. When t cannot be converted to u, the other function test is going to be called. Big, size of big is different from size of small, for sure, and so exist is going to be false. So if conversion exists, if t can be converted into a u, then exist is true. Otherwise, it's false. Okay? So last step, we define a macro that is called, well, actually we can define an additional version of class which just takes t, which also provides same type equal to true, because when t is and u are the same, like then we want to check if same type is true. So define subclass tu checks if t is a superclass of u. So it checks if I can convert u star into a t star, and I cannot convert t star into a void star. So sorry, if t star is not the same as void star, then t is a superclass of u. And I can make it strict by checking if it is a subclass and if u star is different from t star. Okay, so it's a very, very strange technique, I admit, but it allows you to check if one is a superclass of the other. So let's go again and look at the code to understand the trick here. So the trick is to define two different classes, two different types of different sizes. Of writing two functions, the first one returns the small type, the second one returns the big type. The first one allows conversion, the second one allows every kind of conversion. And then finally, to take make t as to take a function that produces a t. Okay, and let's see another implementation of this here. Suppose we want to we want to write a way to check if a certain type is a pointer or not. So we have three cases of pointers. We have simple pointers, or we have member function pointers, or we have function pointers. So There are three kinds of pointers. A pointer to integer, for example, or a pointer to a member function of a class, or a pointer to a function. All of them are pointers. So we want to write a mechanism that checks if a type is a pointer of one of the three types. So how do we do that? Well, it's very simple. Again, we are going to use two types, in this case char and double, that we know are different sides. And then we are going to check, to write three functions. The first one takes a pointer to u, where u is a template. The second one takes two classes, x and y, to check if it is a pointer to a class member. And the third one takes u as a return type to check if it's a function pointer. Finally, the last one, which returns a double, takes everything else. So we define one type t, and we say size of is pointer t equal size of char. The result of this comparison is true or false. We assign it to value, and so basically we are going to print if is pointer int ptr, of course yes, so it's going to print 1. Is pointer foo member ptr, yes, so this will print 1, and is pointer function pointer value, and this again will print 1. So it's a very similar technique for checking if a type is a pointer. So it's something that you can use in general. Probably you will never need to use that in your practice, but maybe you can encounter this kind of techniques in the future when you try to code in C++. So if you encounter this kind of techniques, don't be scared. It's just metaprogramming. Okay, that's it for today. Thank you very much, and then we are going to continue with the metaprogramming next week, so next Wednesday. And also next week we are going to discuss also metasim in a little bit more details. Okay, thank you for today. Do you have questions? No? Okay. So we continue next time. See you. Bye-bye.
Bye. See you.